And an approximate, well, you can do an exact formula using other quadrature schemes. But now, is this Prismoidal formula used at all? And the answer is yes. It's used by civil engineers to approximate the volumes of things that they're going to excavate or put in. I have no idea what the four-dimensional one might be used for. But it should be done. And I still think it's a great problem for a very good high school student. I don't want to work on it myself because I won't learn much. But if you have a very good student, undergraduate or access to a very, very good high school student, I think it's a great problem. And I'd like to see it solved. I mean, it's been around, this formula has been around since the 19th
My
century.
computer will do it, and it must be unaware.
Computer will do it, and but let me warn you, you have to be careful, because one of the things that you can do with this Prismoidal formula is take degenerate cases. And so one of the degenerate cases is, of course, taking the polygon and just be a point. But that's not the most interesting degenerate case. The most interesting degenerate case is to take the top polygon to reduce to a line, and the bottom polygon to reduce to a line that isn't parallel to the first of them. And it works there too. So that's the geometry problem. Now I want to say a little something about some old analysis problems that I worked on 30, 40 years ago. Okay. The integral from 0 to x sine x sine t dt sine at is 1 minus cosine ax over a, and that's non-negative. When x is bigger than 0. That's non-negative always. If you take the simplest analog of that, the sum sine kt, that isn't non-negative, but you can get a non-negative sum out of it in two different ways. If you look at sine k minus a half t, this turns out to be non-negative, and that's what Fair used to prove the positivity of the Cesaro means for Fourier series, and therefore getting the first way of recapturing a Fourier series from a finite number of terms and then letting it go to infinity. And then Fair conjectured that the sum k goes from 1 to n, sine kt over k is positive. And that was proven by Dunham-Jackson and Hagen-Groenewald independently within a couple of years. And there are probably 20 proofs of this. One of them due to Doron that says that if that's non-negative, then this is non-negative unless AK is identically 0. These are all for t bigger than 0. Between 0 and pi. Which really shows that this result with the AK equals 1 is useless. Because anytime you can do something with that, you could have done it with this, which is simpler to do. But it's still an important inequality. And there was an extension of that. Oh, Fair was the first person. Legendre polynomials were mentioned. And Fair proved that. Now, there's an interesting story, and unfortunately I don't remember all the details. I was told by Doron. Fair gave a talk, and Göttingen and Hilbert and Minkowski were there. And the two of them and a third person went out for their regular walk afterwards. And either Hilbert or Minkowski raised the question of, is there a corresponding theorem for spherical harmonics when you do spherical harmonic expansions on the sphere? And this was passed on to Fayer by the third person as a problem. It would have been nice if they'd asked it publicly after the talk, but they may not have thought about it at the time. And Fayer reduced it fairly rapidly to showing this, and it took him a while to do that, but there's a formula due to Dirichlet that gives you an integral representation for Legendre polynomials, which isn't good enough. But there's a variant of it due to Mailer, which gives it to you for free from the corresponding thing for this series. And then Feldheim, Hungarian mathematician who died during the Second World War, in a paper that wasn't published in his lifetime, but it was found by Fayer, or he wrote to Fayer. Fayer didn't do anything about it. But after Fayer died, Doron went through Fayer's papers and found this. And he wrote to Gabor Szego. And Szego then wrote a paper with Feldheim's name on it. And then an appendix that Szego did. Pn alpha beta of x are the Jacobi polynomials. They are polynomials that are orthogonal with respect to this measure on -1, 1. And they can also be represented as hypergeometric functions. They have a generating function, and what Feldheim proved is that the sum k goes from 0 to n, pk alpha alpha of x over pk alpha alpha of 1 is non-negative, or it's positive for x between 0 and 1 when alpha is greater than or equal to 0. And then Szego showed that this passes over to a problem involving Bessel functions. And Szego gave a sharp result here. This is non-negative for alpha greater, for x greater than or equal to 0, and alpha greater than or equal to alpha naught, where alpha naught is, let me call it alpha 2. T to the minus alpha j alpha of t dt. And let me call it 2 alpha. Where this is the second positive 0 of this Bessel function. So what you're doing is you're looking at the area under the first arch and the area under the second arch. And, well, the thing is going to blow up at 0. And this is sharp. Now, I got interested in this from some quadrature problems, and eventually was led to the conjecture that the sum k goes from 0 to n, pk alpha beta of x over pk beta alpha of 1 is non-negative for x between -1 and 1. And you can show that for beta less than -1/2, you can't get it. 1/2 minus 1/2 is the old result of Fayer there. 0, 0 is a Legendre result. 1/2 was the Fayer conjecture that Grunwald and Jackson did. And eventually, George Gasper and I showed that this is true. You go out to -2 and 0. But the interesting case is the Bessel function case. Well, this is of great interest because it turned out when beta is 0 and you have integer values along here, that was the final step that was needed in the proof of the Bieberbach conjecture by Louis de Branche. And I couldn't believe it was true because